Hello everyone, welcome back to ROBT402 Robotic Mechatronics System Design course, Lecture 11, Programming Counters. Today's topics are as follow: PLC counters, programming example, and programming exercise. Counter instructions. PLC counter instructions. There are two main PLC counter instructions: semantic counter functions and IEC counter functions. So as you could see here, we have the IEC ones listed under the counter operation in the basic instruction list, and we have a legacy counters. Those legacy counters are called semantic counters because they are only belong to the semantic PLCs and Siemens PLCs. We have up counters, down counters, and up-down counters. Up counters, each pulse at the counter input increments the count value by 1 unit. Down counter, each pulse at the counter input decrements the count value by 1 unit. And up-down counter, a pulse at the up counter increments the count value by 1 unit. A pulse at the down counter decrements the count value by 1 unit. A data record, which is present in the system data, is permanently assigned to each semantic counter function. This limits the number of semantic counter function. So for every counter that we use for every instance of the counter, we have a data record in the memory, very similar to the timers. Semantic counter functions are global tags. The symbols are declared in the PLC tag table, similar to timers. The semantic counter functions run in startup and run modes. Semantic counter functions as overall function, so you could see it in different language programmings, in the ladder logic, in function block diagram, in structure control language, and in STL. So in any languages we have a different format to use these counters. We don't go to the detail of each language here, and we only focus on the IEC counters. We could use semantic counter functions as single elements, as you could see here, for example, as a coil. We could use it as a count up or count down, or we could have a set counter function or reset counter function. IEC counter functions are as follow. We have count up, count down, and count up down. An IEC counter function is a statement with its own data. When programming a counter function, you specify a data block in which the data is to be saved. This will happen automatically once you declare a counter. That will be declared automatically in the memory. If you select the single instance bottom, it must be a different data block each time. If you program a counter function in a function block, you can also select multi-instance. In this case, the data of the counter function is saved as local instance in the instance data block of the function block. In many cases, during the example and exercises, I recommend you to use a single instance, at least for now. The count value of a counter function can be set when programming for data type as sint, int, dint, lint, usint, uint, udint, and ulint. The data structure of a counter function is dependent on this setting. So you could choose what type of the data block you wish to have based on the based on the type of the input. Program counters serve the same function as mechanical counters. So here you could see a mechanical counter, and here we have actuating lever. So every time we actuate the lever, we press the lever, we basically increment the number here on the front panel of the counter. And every time we wish to reset the number, we just need to press the reset button. Every time the actuating lever is moved over, the counter adds one number. Resetting to 0 is done with a push button located on the side of the unit. Electronic counters can count up, count down, or be combined to count up and down. Although the majority of counters used in industry are up counters, numerous applications require the implementation of down counters or of combination up-down counters. We could choose to have two counters, one up and one down, or we could select a counter which has capability of including both of the up and down counters, and we call them up-down counters. All PLC manufacturers offer some form of counter instruction. One common counter application is keeping track of the number of items moving past a given point. So for example, here we have a proximity sensor, and that proximity sensor counts every item passes by of the sensor. So the sensor sends the pulse. The sensor basically sending the pulse in sensor is analogous to moving over the lever in mechanical counter. So every time we have a signal from the sensor, the counter will count up. PLC counter instructions are similar to timers, except that they do not operate on internal clock, but are dependent on external or program sources for counting. So timers are used based on the internal clock, but not the counters. Counters get the signal from the sources outside of the PLC. Generic coil formatted up counter instruction are shown here. Okay, so here we have an up counter, and here we have a sensor or the switch that sends the signal. Every time that the sensor goes from false to true, the accumulated value will increment by 1. This is a preset counter value. Once the accumulated value reaches to the preset value, the output of the counter will be true. And of course, similar to the timers, counters also should have an address in the memory. We need that address to recall them through all the program. The counter reset instruction must be used in conjunction with the counter instruction. The counter reset coil is given the same address as the counter that it is to reset. Up counters are always reset to 0. So here we have that logical signal that increment the value of the counter, and we have this reset counter switch, and this coil is specified and assigned solely to reset the counter. Generic block formatted counter. All PLC counters operate or count on the leading edge or off to on transition of the input condition. Okay, so off to on, so this is let's say the proximity sensor. It could be a, let's say, inductive sensor, and every time that the sensor goes off to on, we have a signal. This is our counter, and we have a preset value. Once the accumulated value reaches to the preset value, the output will be true. If we wish to reset the counter, we need to press this button, or we need to reset it intentionally. It won't reset automatically. PLC counters can be programmed to count up to a preset value or to count down to a preset value. The up counter is incremented by 1 each time the rung containing the counter is energized. Here we have a limit switch, we have our counter up, and here is the signal. Every time it will increment up. So you see that so far we had 1, 2, 3, 4 pulses, and the accumulated value is 4. The down counter decrements by 1 each time the rung containing the counter is energized. So here we have 5 pulses, and we have a -5 because we have a counter down. Okay, so for both of these cases, once the accumulated value is equal to the preset value, the output will be true or on. Up counter. The up counter is used to count false to true transition of an input instruction and then trigger an event after required number of counts or transitions. So here we have a bottle of milks, and we have a sensor that sends signal to the up counter. The up counter output instruction will increment its accumulated value by 1 each time the counted event occurs. So we are repeating the same concept over and over again in different slides and in different formats, just to make it solid in your memory that what is a counter. Okay, so here we have one example, and in this example we have an up counter. We have this push button 1 here for counting, and we have a push button 2 for resetting the counter. The preset value is 7. We have red pilot light and the green pilot light. Once the counter is done, so once the accumulated value reaches to the number 7, the down bit of the counter will be true and the red pilot light will be on. Before reaching to the number 7, once the down bit is still false, green pilot light will be true. So from number 0 to number 7, the green pilot light, sorry, 0 to 6. From number 0 to 6, the green pilot light will be on. Once we reach to the number 7 and beyond, the green pilot light will be off and the red pilot light will be on. We need to press the push button 2 to reset the counter and reset the pilot lights as well. Up counter timing diagram. So in this diagram, you could perfectly see how the up counter in the previous example works. Here is the count pulse or the push button 1. So you see in the rung 2, which is the down bit of the counter, is false. Once we reach to the number 7, the down bit will be true. In the rung 3, which is the negated value of the down bit, is a true before reaching to the number 7 and afterward is false. And rung 4 is the reset push button is not pressed until here. Okay. Here we have an accumulated value that each time we have a signal, it will go up until it reaches to the number 7, which is the preset value. And when it reaches to the preset value, the down bit will be true or negated down bit will be false. Now at this point, the operator has decided to press the reset button. So the reset button is pressed. Now everything will be resetted. So you see that the down bit now will be false, negated down bit will be true, and the accumulated value will drop back to 0. PLC counter program used to stop a motor from running after 10 operations. This is another example to comprehend the concept of a counter. We have input here, which is stop push button, we have a start push button, and we have a reset push button. So these are the physical push buttons on the panel: start, stop, and reset. And as output, we only have one, which is our motor. Now, if you press the start button and the down bit of the counter is still false, so it means that we haven't reached to the preset value of the number 10, the motor will start to run. Okay, so and we have a shunt here. It means that once we press the start button, the motor will keep going no matter what is the position of the start button afterward. Now the motor has started once, and the status of this contact will go from off to on. So the accumulated value of the counter will increment by 1. So we'll go to number 1. Now assume that the operator has decided to stop the motor. Okay, so stop push button is pressed, motor is stopped, and again started over. When that happens, the counter will count up again and the accumulated value will go to 2. So no matter what is the interval between each operation, we only care about the number of time we have started the motor. Once it reaches to the number 10, which is the preset value of the counter, we won't be able to start the motor again. Why? Because the down bit of the counter here will be true and the negated of that will be false. So we won't be able to start the motor. If we wish to start the motor again, we need to reset the counter. Once the counter is resetted to 0, then again we could start over and operate the motor for 10 times. Can counting program that uses 3 op counters. We have cans, Pepsi or Coke cans, for example, and we have a proximity sensor. Proximity sensors will count cans, and we have a reset push button. We have 2 counters for counting parts. The first one has a preset value of 10, and the second one has a preset value of 32,767. This is the maximum number of parts we could count in this specific PLC. We have another counter here for counting number of packages. Okay, so we could put 10 parts in one package. So once the downbeat of this part will become true, then we will put those 10 parts in one package, and we have one package. Okay, so here, once the downbeat of the 5-1 is true, we will close the box. Once we have closed the box, then this contact will be true, and the accumulated value of the packages counter will increment by 1. We could reset. The 5.2 and 5.3, these two 5.2 and 5.3 packages by manual or separate reset push button. However, for the 5.1, we need to reset this counter once the box is closed. A one-shot or transitional contact is often used to automatically clear or reset a counter. The one-shot can be triggered from a momentary signal or from a signal that comes on and stays on for some time. It stays on for one scan only and then goes off. It stays off until the trigger goes off and then comes on again. So here, let's say we have one input here, and this program shows us how one-shot output works. So at the beginning, when the input goes from false to true or off to on, this internal relay contact, that is not a physical relay, this is an internal relay. This internal relay contact is true because the internal relay contact itself is false, but the negated contact of that internal relay is true, so the one-shot output becomes true. In the next rung, since the trigger input is still on, the internal relay coil will turn to true. Now, in the second scan, the internal relay coil still is true, and the negated value of that one will be false. So the one-shot output will become false. So it shows how it works. However, If you use the one-shot output or the transitional, one-shot, yeah, coil or the transitional coil, you don't need to use this internal memory. It includes that internal memory. It's programmed inside that, and basically it works only for one scan only. Some PLC provide transitional contacts or one-shot instructions. The off-to-on transitional contact provides a one-shot pulse when the trigger signal makes off-to-on transition. So this is the symbol and this is off-to-on transition. When we press that bottom A in the previous slide, for one scan only, we will get a true output or status on the coil. And for the on to off, it's completely opposite. When that push button goes off from on, for one scan only, we will get a true pulse at the output. Alarm monitor program. Again, this is another example to see how the counters work. Here we have combination of counters and timers. We have two timers here and we have one counter. Let's look at the inputs, what we have. The input, we have this switch which basically measures the level of water here. Okay, so once the level of water reaches to specified value, then this FS switch will be true. We have one SS switch or switch status switch, which we could turn it from off to on. Okay, so we could turn the system off or on. And what we have here, we have a light, alarm light. It's a siren basically. Okay, so this alarm light should flash. That's why we coupled two timers here, and we have a annunciator before in previous lectures. Review the annunciator that we need to use a downbeat of the other counter as an input of the next timer for the next for the input of the next timer, and the negated downbeat of the second timer for the first one. These two are to create an annunciator. Now, once the level of water reaches to specify value, Fs is true, and the accumulated value will increment by 1. Here we have used a preset value of 1, and we could change it, of course. Once it reaches to the preset value, then the downbeat of the counter, which is here, will be true. When we have a downbeat of the counter true, and we use the downbeat of one of the timer, then the light will start flashing. Okay. And here we could reset the counter. Down counter. A down counter will count down or decrement by 1 each time the counted event occurs. Here we have 3 push buttons, 1, 2, and 3. One is used for up counting, the other one is used for down counting, and the third one is for resetting the counter. Again, we use a preset value, and we need to reach that preset value to get true output or to have this light on, normally the down counter is used in conjunction with the up counter to form an up-down counter. Okay, so here we have this nice graph that shows how that up-down counter works. Let's say we push the up counter 6 times and then we started to press down count push button for 4 times. Here we have the accumulated value that will increment to 6, and once we pass threshold 3, because this is a preset value, then the output will be true. It will stay true until it will drop down below 3 again. So once we reach to the number 2, by keep pressing the countdown push button, then the output value will drop to 0. And everything will be reset to 0 once we press the reset push button. Once we press the reset push button, the accumulated value will drop to 0 again. Parking garage counter program. We have one switch in the entrance, at the entrance of the garage, and we have one exit switch at the exit port of the garage or exit door of the garage, and we have one reset push button. When a car passes through an entrance door, then the up counter will count up, and once a car exits from the exit door, the down counter will count down. And look, we are using same counter, so you see that the address is the same, is C51. It means that this counter is up down counter, and the preset value is 150, maybe because the capacity of the parking is 150 cars. We cannot have more than 150 cars inside the parking. So once the accumulated value reaches to the preset value 150, the down bit will be true and the lot full light will be on. Okay, so it shows the new driver that the parking is full and there is no more room for parking. And we have a reset push button. If something goes wrong, if these sensors, let's say, fail to count properly, we could reset the system to 0. Another example of up-down counter program, we have push button 1, 2, and the reset. Push button 1 is for up counting, push button 2 is for down counting, and we have 3 pilot lights. Okay, and we are using one up-down counter. Once we are counting up, and the output A will become on. Once we are counting down, output B, and once we reaches to the preset value 10, the output C will be true, and we could reset the counter immediately once we reach to the preset value by this input C, by this push button. Program that provides continuous monitoring of items in process. So Here we have material processing system. Okay, could be, for example, uh, temperature processing of some sort of metals. Okay, and we have in-feed parts and we have out-feed parts, and processing system has specified capacity. The accumulated count of the counter continuously indicates the number of in-process parts. So here we have the program, in-feed count, out-feed count, and we have a reset. And the accumulated value of the counter shows the number of in-process parts. Cascading counters. Depending on the application, it may be necessary to count events that exceed the maximum number allowable per counter instruction. One way of accumulating this count is by interconnecting or cascading two counters. So it depends on the PLC, the hardware and the software. And the maximum number could be limited in some cases. Then we need to use these techniques. Counting beyond the maximum count number. So assume the maximum count number is 32,000 and you want to count beyond that. How could we do that? We could cascade and use two counters. One is 5-1 and the other one is 5-0. Every time we press the push button 1, we are up counting this 5-0 counter. Once it reaches to the preset value, the down bit will be true, and then we could start counting on the second counter. So by this technique here, we could count up to 64,000. Or we could cascading counters for extremely large counts. So we have the first counter that counts until 500 and the second one again until 500. However, here we are cascading. So first, the down bit of the first counter is not true, so we are not using this counter, and this counter will increment up until it reaches to the 500. Once it reaches to the 500, the down bit will be true and we will start counting here. Okay, so here once the down bit of the first counter is true, we will reset the counter by the down bit of itself. So this one will be resetted to 0. Okay. Once it resetted to 0, the down bit will back to false, and again we will start to use the same counter. So what happens? We incremented up to 500, then we accumulated here, or we incremented here only once, and again this one reset it to 0 and is starting over from 1 to 500. Again, once it reaches to 500, this one will increment to 2. So you see that every number here represent 500 counts, and the maximum that we could count is 500 by 500. And if we increase this preset values to the maximum value, we could reach to extremely large numbers. 24-hour clock programming, we are basically using um, counters for counting minutes and hours, and here we have a retentive timer. That retentive timer is a use basically we are using that one because we need to have access to the external clock of the system, okay, to have a perfect representation of the time. So every time this timer, which we are using for seconds, reaches to the 60, which is the preset value of 60 seconds, the minute will increment once up, and once we reach 60 in the minute, the hour will increment up. So if we look at the accumulated value of the hours up counter and the minutes up counter and the second retentive timer, we could say what is the time? How many hours has passed? Incremental encoder counter applications. The incremental optical encoder creates a series of square waves as its shaft is rotated. So here we have a motor, and here is a back shaft, okay, or back rotor shaft, okay. We don't have a gearbox here. The gearbox is in front of the motor. We don't have a load here. The load is on the other side of the motor, okay, and here, which is not shown, okay. Here we only have one optical encoder. And what is that optical encoder? There is one disc. That disc is connected to the rotor and rotates with the speed of the rotor. Okay, on the disc we have some lines and there is one the optical source or the light source, and every time each line or a slot passes, it will block the light source, and again it will be released between each slide. And there is one optical sensor that will receive the light. So that optical sensor will generate this pulse, and we need to count those pulses to basically measure the rotation of the rotor. The encoder disc interrupts the light as the encoder shaft is rotated to produce the square wave output waveform. Cutting objects to specified lengths. Now we want to use that encoder to cut our woods with specified lengths. So the speed of the conveyor is constant, and since this motor is rotating the conveyor, so also the speed of the rotor here is constant. Because the speed is constant, we need to count specified number of poles to have a constant length for each wood. So the object is advanced for specified distance and measured by encoder pulses to determine the correct length for cutting. Now let's see how we could use the counter program for length measure. We have a magnetic sensor here, okay, and that magnetic sensor for this example works the same as the optical encoder, because we have a sprocket here, and every time that one tooth of the sprocket passes by of this magnetic sensor, we have one pulse. Okay, so this magnetic sensor is creating that pulse similar to the optical sensor in optical encoders. So the magnetic sensor is sending pulse, and let's say we have this photosensor. This photoelectric sensor is also false because we don't want to have wood. Okay, what is the type of this photoelectric sensor? Is a retroreflective ones. The preset value is 10. Once it reaches to the preset value, then we could either cut, or we could be sure that we have a proper length based on the application, and then we could reset the counter. Combining counter and timer function. Automatic stacking program. In this program, you see that we have conveyor 1 and we have conveyor 2. Conveyor 1 will bring metal plates into the conveyor 2, and on the conveyor 2 we are stacking, and once it's complete we will move forward to stack another pile of metal plates. So here we have one light sensor that shows off if the stack is reached to its up value. We have stop bottom, start bottom, and the foot sensor. Okay, so we have one timer for the M2 conveyor, and we have one counter for number of plates. So the photosensor will send signal to the up counter to increment value of the up counter, and once it's reached to the preset value 15, it means that the stack is full and we need to move forward. So once the down bit of the up counter is true, then the M2, or the motor of the conveyor 2, will be on to move the stack forward. Okay, so we need to move the stack forward for 5 seconds. After 5 seconds, the down bit of the timer also will be true, and once the down bit of the timer is true, then we could reset the counter and we will stop the motor. Or we could press the stop button. Alternatively we could press the stop button and reset the counter and stop motor. Product flow rate program. This is another program. We will count the product rate. Here we have a sensor that counts the cans, and every time we'll count up the up counter. However, the down bit of the timer should be false. Okay, once the down bit of the timer becomes true, it means that the 60 seconds is passed, and then it will stop counting. So In 60 seconds, we counted the number of cans so we could have the flow rate of the cans passing by of the sensor. So for example, if we count uh, 20 cans in 60 seconds, the flow rate will be 20 divided by 60. Timer driving a counter to produce an extremely long time delay period. We have timer and counter, and the preset time value of the timer is already high but not enough to satisfy your needs, is 10,000. Once the accumulated value of the timer reaches to the preset value of 10,000, then the down bit of the timer becomes true and the counter will count up. Then here we have negated down bit of the timer as an input. So it means that once the timer is finished and the down bit becomes true, then the negated value will become false and it will reset the timer. The down bit become false, and then again it will become true. And then again it will time, and the accumulated value will go up, again reaches to the 10,000 and the counter will count up. So what is the overall elapsed time is accumulated value of the timer multiplied by the preset value of the timer plus the accumulated value of the timer. This is the overall elapsed time, and we could reach extreme large value for the time because we could increase the value, the preset value of the counter and timer, and multiply them together. It will be enormously high. In this slide, we are going to start programming timers and counters in the distribution station. However, we will use a simulation. You are going to modify the project that you created in the previous lecture and include timers and counters to change the way that the station works. I recommend to program over from the beginning, follow the steps, and include all the contacts and coils and rungs that will be presented in these slides. The changes are like this. Once the start button is pressed, the piston will be actuated to deliver a part. Then the swivel drive will move to the magazine position to take the part. The swivel drive will take the part to the downstream position and leave it there. Then it will come back to take another part. In total, 4 parts will be moved, and then the system will stop. So we need a counter for these 4 parts here. Once the start button is pressed, the process will start over. Whenever the stop push button is pressed, the swivel drive will move, remain in the downstream position. There will be time delays for the swivel drive to move between 2 positions. So here we have timers. Modify the PLC program, adding one on-delay timer. Again, you may not have this program before, but you could include all these contacts and coils. So don't try to modify any previous program. Try to start over and program it since the beginning. You have a start button, stop button, start LED, and start LED. We are using also LEDs of the start, stop, stop and reset buttons. Drag and drop it in the network 2 in the place shown with green small square. Okay, so once you click on timer, drag and drop it, then you will see the box. So it was network 1. Here we are developing network 2, including the start LED. Pick a name for the timer and click on OK. So once you drop it, you will see the box, plus you will see this call option to create a single instance of a timer. You need to give it a name, specify 4 seconds as the preset time by typing T sharp 4 seconds here in the preset time. Add a contact and introduce a second TON block, call it TON2, set PT as 4 seconds. So still we are in network 2. After this rung, you need to create this rung, contact, a timer, and now we need to modify it, and this configuration of TON blocks will generate square wave form 4 seconds off, 4 seconds on. So it's very similar to that annunciator that we developed and we discussed before, a combination of 2 on delay timers. You see that we are using down bit of the first timer as an input to the second, and the negated down bit of the second timer as an input to the first timer. As the output of the TON01 and the short pulses every 8 seconds as the output of the TON02. So now we could have a flashing with the interval or period of 4 seconds if we use a downbit of any of these timers in the proceeding runs. Locate the up content counter CTU in the list of a basic instructions. So basic instructions under counter operations, we have count up. In network tree, you're gonna drag and drop it here. Once you do so, you need to change or give it a name here. Give it the name of CTU01, complete network tree as below. Preset value is set to 5. There's a preset value of the counter as we want to perform the given task 4 times. Okay, so why then you need to have preset value of 5, although we need to count 4 times. Think about that. I'm gonna leave that to you. Negated stop button is used to reset the counter. Okay, so we need to always to have some sort of input to the reset, and that is going to be done by the reset as it was given in the description of the problem. And distribute piece is used as the count up input to count the number of pieces moved. This is the distribute piece. So what is that distribute piece? This is the piston underneath of the magazine in the distribution station. Every time that distribute piece actuator moves forward, we have a piece provided for the swivel. So that swivel will come and will pick the part. Add the contacts to network 4 as below. So here we are in network 4. Try to develop it as you could see here. We have start LED. We have the down bit of the timer 1. We have the down bit of the up counter 1 negated here, and we have this is a display initial position LED. It's a display initial position LED. So this network means that as long as the start LED is on, start push button is pressed, but stop push button is not pressed, and the counter has not finished counting, the display initial position LED will blink 4 seconds on, 4 seconds off. Why it will start to blink? Because of this down bit of the timer, because we created the annunciator before in the previous networks. Now in the network 5, write the following code. In this way, a part will be distributed. Okay, so here we have distributing part, then the swivel will come to the magazine position to take it. So this is basically swivel to the magazine position to take it, where the vacuum will be set to pick it up. Okay, so here we are setting the vacuum because we want to keep the vacuum on through all the course of the movement of the swivel. Then the swivel will move to the downstream position. How it will back to the downstream position? By this coil. Okay, so you see that either this one works or this one. If it swivel to the magazine, then swivel to the downstream will be false, and once this one is true, this one will be false, because these are antagonists, they cannot work at the same time. What is this one? This one is a swivel to magazine sensor. Okay, so this is the sensor, or to be precise, this is a limit switch. This is a limit switch on a semi-rotary actuator, pneumatic semi-rotary actuator of the swivel on the magazine side. Okay, so once we are on the magazine side, this sensor is true, we will set the sensor. Once we are on the other side, on the downstream, then this swivel to magazine, the negated swivel to magazine is true, and we could provide a piece. Once we are in the magazine, we cannot provide a piece. Locate TP, this is a pulse timer block in the basic instruction list, drag and drop it to network 6. Okay, so here underneath of timer operation, locate TP and drag and drop it to the network 6 here. And then you will have the call option, give it the name TP01. In the network 6, you have a TP and then you have swivel to downstream. This is a micro switch, again on the pneumatic semi-rotary actuator of the swivel. Once we are on the downstream, okay, once we are on the downstream, which is the other side, and we need to drop the part, then the TP will be active for 1 second. Why do we need that? So we are using the down bit of the TP timer to reset the vacuum, because we need to first reset the vacuum. We have that suction cup, that vacuum should be off, plus at the same time we need to eject the piece. So we need to first turn off the vacuum, then we need to blow out air to release the part from the suction cup. And this is the eject piece, that blowing air to release the part. The output of the TP will become on for 1 second each time that its input becomes true, which is when the swivel is in the downstream position, then the part will be ejected and the vacuum will be reset. Okay, now you have 6 networks. If you have followed all these slides, you should have a complete program. Now simulate your project and make sure it works as you wish. Then you can get connected to the distribution station and test it in practice. You don't have access to the distribution station, but you could do the simulation by PLC sim. Refer to the lecture notes of the previous session to refresh your knowledge about PLC simulation and connection. You have a programming exercise. Now it's your turn to write your own PLC program to perform the following task. You may need to define new tags referring to the I/O devices or some internal coils. You should also use the counters and timers in your code. To start the process, you need to press the start push button 3 times in a row. So we need a counter here to count that 3 times of pressing push button. The number of parts to be taken will vary in a sequence. In the first execution, 6 parts will be moved. Then after start push button is pressed and start push button is pressed 3 times, 4 parts will be transferred. The process will continue with moving 6 and then 4 parts in the next run. So we are basically switching or intervaling between 4 and 6. First time we are moving 6 parts, next time 4 parts, and again 6 and 4 and 6 and 4. You can use move operator. This is the move operator to specify the PV, which is the preset value of the counter. See below as an example. So here you see that as an okay, so here we have an input, let's say 5, and the output is the preset value of the timer. Every time this move box is enabled, the in value will be transferred to the out value, and the out value is the preset time. Okay, so you may have 2 move box, one with 4 and the other one with 6 input, and you need to enable it intervally to set the preset value of the timer. Make the initial position LED, which is the reset LED, blink with the higher frequency 1 second on and 1 second off. So you need to work on this exercise simulated on TIA, okay, PLC, and once you have simulated that, tested, then you could submit it on Moodle.